Okay, so this is Mr. Vitale, and I will be showing you how to solve the first extra problem for the horizontally thrown projectile. So the first problem says, some believe that being hit with bird droppings is a sign of good luck. Cesare was sitting on the beach contemplating the quantum tunneling effect when Tim screamed, "Watch out!" in his booming voice. The bird was traveling 11 meters per second when it relieved itself. If it is 50 meters above Caesar's head, where would Caesar have to stand to be hit by the droppings relative to the point where the bird dropped? So, first thing I think we should always do is start by drawing a picture. So, you might draw a bird. I'm going to draw a circle because I can't draw a bird. But basically, the bird's going at 11 meters per second. At this point, we'll say, is the point where it dropped its stuff. We'll draw that with another circle. And we know that this is also going to be moving at 11 meters per second, right? Because it was inside the bird at that point. So when it drops it, it's also going to be going at 11 meters per second. Basically, we want to know where Caesar has to be in order for that to go right on his head there. We have a displacement above his head, right? Because we're looking at his head as being 0, basically. And so we have this is 50 meters high. So now what we want to do is we want to start filling in our givens. So since we have x and y direction, we want to solve for both of them. So we're going to put one of these guys. We have delta x, v initial, v final acceleration and time, and then delta y, v initial, v final acceleration and time. So the delta x is going to be how far this stuff goes. It's going to start from 0, we're going to call it, and go all the way over to Caesar's head. So we're not sure, that's what we're solving for. The v initial in the x direction is going to be the 11 meters per second. Since we know that throughout this whole trip in the x direction it's going to stay constant, we know this is also going to be 11 meters per second, and in the same breath we can say that this is going to be 0 meters per second squared. It's not going to accelerate in the x direction, and one of the ways you can remember that is because we're going to need something to either push it one way or the other. Either you have friction or you have rocket thrusters on the object. In this case, we're assuming that there is neither. So therefore it's not accelerating in the x direction. However, when we come over here to the y direction, we do know that it's accelerating. It's accelerating due to gravity. That's going to be a negative 9.8 meters per second squared. Why is it negative? Well, which direction is it going? We define down as being negative. So if you're accelerating downwards, then it's going to be a negative 9.8 meters per second. Delta y is how high this thing is, and we have to be careful because we're saying v final minus v initial. The final landing point is going to be here on Caesar's head. That's at 0. So 0 minus 50 is going to give us a negative 50. That negative is important because we need to put that in the equation correctly, or else we're going to get different numbers. Now, whenever you drop an object, and this also goes for horizontally launched projectiles, the v initial in the y direction is going to be 0. If you can just imagine something starting off in your hand and then dropping it, the very first speed it's going to have is going to be 0, and that's when acceleration starts to act on it. So then it starts to speed up from there. But at first it starts out at 0. That's the very first speed it has. V final we're not sure, and to be honest, we're not really asked for it, so we don't care about it. Time we're also not asked for, but now here's the problem. Your next step, or the next logical step, would be you're trying to solve for the delta x. You would just say, well, I have 3 givens here, 11, 11, and 0. Why don't I use one of the 3 equations that I know to solve for it? I'll write down the 3 equations that we have. We have v final is equal to v initial plus at. V final squared is equal to v initial squared plus 2a delta x. And then we have delta x is equal to v initial t plus 1/2 at squared, where the x's can be replaced with y's if they need to be. In this case, we would say we don't care about time, and we have v initial, v final acceleration, and we're looking for delta x, so we're going to go to the equation that does not have v final in it. That equation would be this one. However, notice that when you plug in 0 for, oh, I'm sorry, this one doesn't have time in. We don't care about time, so we wouldn't use this one. We would use this one. But now notice that if you plug in 0 for this whole term here, the 2a delta x, actually would go to 0 because acceleration is 0, and 0 times anything is 0. So we would just get v final squared is equal to v initial squared, but we know that already because 11 squared is equal to 11 squared. So that wouldn't do us any good. So we do know that the time in the x direction and the time in the y direction is going to be equal to each other. So what we can do is we can solve in the y direction for time, and then bridge that over here, and then use time to solve for x. So then what we'll do is we'll find the time in this direction. So we care about time, we're looking for that. We have acceleration, but we don't care about v final. That's going to be this equation here. So we have delta y is equal to v initial t plus 1/2 at squared, where a is just going to be the acceleration due to gravity. Notice I changed this for the y direction. We are only using y variables in this equation. You can never mix the two variables together. So anyway, you plug in your negative 50, very important that you keep the negative. I'm not going to use units as I plug these into here, but we can see how the units will come out to what we want them to be. But v initial is going to be 0, so this whole term is just going to go to 0. And so you have 1/2 negative 9.8 t squared. So I have my calculator with me. What you would do, I mean, you could do this a number of ways, it's all math, but you just do 0.5 or 1/2 times negative 9.8, and that gives you a negative 4.9 t squared is equal to negative 50. So you would divide both sides by negative 4.9, and when you do that, you get a t squared is equal to 10.2 approximately, and that'll actually give you seconds squared if you follow the units. But then in order to get t by itself, you just square root both sides, and you end up getting t is equal to the square root of that. I'm sorry, my calculator is giving me problems here. It's still giving me problems. Sorry about that. So it's about 3.19 seconds. So that's our time. We can plug that in up here. And now we have enough information in the x direction to go ahead and solve. You can do this one of two ways. You know that the speed, or the velocity, is just the definition of it is your change in x over change in time, and that's for average velocity or velocity that is constant. Since we know that the x direction has constant velocity, we can use this equation to solve for delta x. Or you can just end up using this equation. Notice that when you plug in 0 for this will go away, and you're left with delta x is equal to v initial times time. Same thing here. If you multiply time over here, you get time times v, like this, is equal to delta x. So either one will give you the same thing. So finally, I'll just do it over here. We have delta x is just going to be equal to the velocity, which is 11, times the time, which is 3.19 seconds. And we get about 35 meters, right? So displacement is meters. So Cesare would have to stand about 35 meters away from where the bird originally dropped its stuff.